Hello students, welcome to Diksha Karnataka YouTube channel. So I am going to discuss semiconductor electronics chapter in our Chakravyuh series, and also if you just joining us now, you should know that I have released a complete 215 questions MCQ, that is a marathon consisting almost 4 hours of runtime. So if you want to check that out, then definitely you can do that as well there, but you have to remember that in Chakravyuh the number of questions per chapter is more, total time, total watch time is more, so that is why it was done in a recorded format with all the MCQs basically in one single shot, approximately 15 MCQs per chapter. Okay, so a lot of varieties are there, and if you want to practice quickly just before your exam, definitely you can run it at as 2x speed or 3x speed, and you can not 3x speed, that will be insane. 2x speed is sufficient. You can run it at 2x speed later time and watch it before your exam to revise it quickly. Okay, or if you want to chapter some particular chapter, then you can check our Chakravyuh series. Obviously here we have done all the MCQs covered in that longer version of the video, but it is in a chapter format, it is within a conversation format. Hi Shagupta. So as I said, this is for MCQ 30 questions we are going to do today, and in the longer format video where it is a 4-hour complete marathon video, there we have done 15 questions per chapter, but that was a focused video for all types of students. If you are attempting Chakravyuh, all the chapters, if you have attended, all the questions you have attempted, then definitely that video you can skip. But otherwise, if you have missed some videos, some chapters, you can check that video if you have want to revise it before your exam. Now, so let's see the questions from this chapter. Following pairs of elemental semiconductors, silicon and aluminium, silicon and germanium, silicon and cadmium, aluminium and cadmium. Very easy question. Hi Ujjwala. Hi. So answer this question number 1, easy, and you know the rule. Yes, Shagupta, 1B, silicon and germanium are the two elemental semiconductors. There are no other elemental semiconductors. Okay, elemental semiconductor means semiconductor which are in elements form. Okay, you know the elements and compounds in chemistry, right? There are many compounds, a lot of compounds are there in semiconductor part, but elemental semiconductor is basically silicon and germanium, only two elemental semiconductors. Now question number 2. The energy band determines the electrical conductivity of material is conduction band, energy gap, valence band, all of the above. Okay. So interesting. Let's see who answers this. Hi Aishwarya. Yes, 1G is correct. Shagupta saying all of the above. Yes, so even though conduction band, you need electrons in the conduction band, but how many electrons are there in the conduction band, that depends on the energy gap, and obviously how many electrons you are releasing from valence band as well. In case of semiconductors, we know that valence band plays a major role, so definitely all of the above is the correct answer. Okay, so valence band also have holes in case of p-type semiconductor, so definitely valence band also plays a role, if you wondering that valence band does not play a role. So all of the above is the answer for this question. Next, question number 3. In an intrinsic semiconductor, the number of free electron is greater than number of holes, lesser than number of holes, equal to number of holes, more than number of atoms. Okay. Answer this question, Shagupta, Ujjwala and Aishwarya. What will be the answer for this question? Easy. 3C, equal to number of holes, easy question. So let's not waste time. Let's move on to the next question. The electrical conductivity of pure germanium can be increased by increasing the temperature, doping with acceptor impurities, doping with donor impurities, all of the above. So how can you improve the conductivity? How can you improve the conductivity of a germanium. Okay, germanium is a pure semiconductor. How can you improve its conductivity? By increasing the temperature, doping with acceptor impurities, doping with donor impurities. Donor impurities basically means n-type semiconductor, acceptor impurities means trivalent, that is basically p-type semiconductor. So what will be the answer for this? The answer for this will be all of the above. All of the above. You can change the temperature and its conductivity will increase. If you increase the temperature, as we know, semiconductors behave opposite to that of the regular conductor. So if you increase the temperature, its conductivity will increase. Increasing conductivity means it's that is also part. Now doping with acceptor impurities means you are increasing the holes. More number of holes it can carry electricity easily, conductivity increase. Again, doping with donor impurities, basically you are doping with electrons, extra electrons, you are injecting its free electrons which can conduct electricity. So then again it is also improving its conductivity. So all of the above is the answer for this question. Now, when the electrical conductivity of a semiconductor is due to the breaking of its covalent bonds, then the semiconductor is said to be donor, acceptor, intrinsic, extrinsic. Interesting question. So the conductivity is due to the breaking of its covalent bond. Very interesting question. I will wait. Yes, Ricky, yes, all of them are correct. Ricky, mention the question number and the option, that will be better for you. You don't need to type the entire thing. And this is a very interesting question. I will wait for 5 seconds for your response. Then I will see what is the correct answer for option 5. Question 5. No one? So breaking of covalent bonds basically means it is an intrinsic semiconductor. Intrinsic semiconductor releasing the extra electron, and that electron is contributing towards the conductivity. So it is an intrinsic semiconductor. Okay, be careful. It is neither donor nor acceptor, and definitely not extrinsic. The valency of impurity added to the germanium crystal in order to convert it into a p-type semiconductor is. So what will be the valency of the impurity that you should add to convert it into a p-type semiconductor? So p-type means you are basically adding a acceptor level. So acceptor level means it can accept one electron and sit in quiet in its place, and it can give rise to a hole into the band structure, right? So obviously it will be a trivalent. Substance give you p-type, pentavalent gives you n-type. Next question. The majority charge carriers in p-type semiconductors are, so p-type semiconductors, as mentioned, they basically operate on the holes. So the majority carriers are holes, right? Now let's move on. If you don't answer, I will skip on. If you want to answer, mention in the comment, okay, without waiting, so that I will go a little slower. A semiconductor doped with a donor impurity is, so donor impurity means again it is giving electrons. So giving electron means it is an n-type semiconductor, right? So a p-type semiconductor can be obtained by adding arsenic to pure silicon, gallium to pure silicon, antimony to pure germanium, phosphorus to pure germanium. So gallium is a trivalent. So they basically two, rest of them are pentavalent. To get a p-type semiconductor, you have to add gallium to pure silicon. The thickness of depletion layer approximately is, the thickness of the depletion layer approximately is 1 micrometer. Okay. The diffusion current in a PN junction is greater than the drift current in magnitude. So drift current is what? Drift current is basically because of the applied electric field. Okay, and diffusion current in a PN junction is greater than the drift current. So when you the diode is in forward biased. Okay, what is happening, the drift current is trying to take the current in the forward direction, and diffusion current is going in the opposite direction, right? But in case of forward bias, diffusion current is basically greater than the drift current. In case of reverse bias, the drift current is more because high electric field is produced and it is exceeding the diffusion current. Okay, so it is if the junction is forward biased, the drift current is less compared to diffusion current. Next question, when a PN junction diode is reverse biased, electrons and holes are attracted towards each other and move towards the depletion region. Electrons and holes move away from the junction depletion region. Height of the potential barrier decreases. No change in the current takes place. So when the PN junction is reversed bias, current is not flowing in the circuit, so definitely no change in the current takes place is the correct answer. Okay, electrons and holes generally do not move when the diode is reverse biased. The cut-in voltage for silicon diode. Cut-in voltage for silicon diode is 0.7 volts. The PN junction diode is used for an amplifier, a rectifier, an oscillator and modulator. It can be used in many ways, but rectifier is the primary function. The output of the full wave rectifier is pure AC, pure DC, pulsating DC, pulsating AC. So the output of a full wave rectifier, if you see, a full wave rectifier generally gives you this kind of output, right? This is the waveform. But what is pure DC means? Pure DC, I informed in the past also when teaching semiconductor physics, that pure DC is basically a straight line. So straight line, but you are not getting that straight line, it is pulsating, it is increasing and decreasing. So basically it's a pulsating DC. Okay, pulsating DC. Next question, the forbidden energy band gap in conductors, semiconductors and insulators are EG1, EG2 and EG3. Okay, so conductors is EG1, semiconductors is EG2 and insulators are EG3. So respectively the relation among them, what is the relation among them? So EG1 is basically a conductor, so definitely the band gap will be smaller for EG1, so EG1 will be smallest. Okay, almost 0, and EG2 will be in between and EG3 will be highest. So definitely option C is the correct answer for this. Okay, the energy band gap in germanium and silicon in electron volt respectively. So the energy band gap is different than cut-in voltage. Energy band gap is in electron volt and whereas the cut-in voltage is in volt. So you have to be careful about it. So for germanium it is 0.7 and for silicon it is 1.1. Okay, the band gap is 0.7 for silicon, 1.1 for germanium. I think during my long video I made this mistake by choosing this because the order was given in a different order. Okay, so be careful, it is 0.7 and 1.1. Next, in a semiconductor, the concentration of electron is 8 into 10 to the power of 14 centimeter cube, and that of the hole is 5 into 10 to the power of 12 centimeter cube. The semiconductor is. So how to calculate the semiconductor is p-type, n-type, intrinsic, PNP type. So what is the concentration of electrons? Concentration of electrons is 8 into 10 to the power of 14. Okay, concentration of holes are 5 into 10 to the power of 12. So definitely it's not an intrinsic semiconductor. In case of intrinsic semiconductor, the concentration are same. But if you see that number of electrons are much more than that of the number of holes. In fact, if you divide it, you will see that number of electrons are basically 800 times more than that of number of holes. So obviously number of electron is dominating. So number of electrons is dominating means it's an n-type semiconductor. Now next question, which of the following energy band diagram shows the n-type semiconductor? So n-type semiconductor basically has an intermediate level from where electrons can easily go to the conduction band. Okay, whereas in case of p-type semiconductor there is an intermediate band where electrons can easily jump to and creating holes in the valence band. Okay, so if you see the diagrams, okay, first of all the conduction band should be the first and should be in the top, and valence band should be below it. So only these two options we will consider. We will not consider this one and this one because they have wrong order. Valence band is coming first, conduction band is coming last. Right, now if you see that in this case band gap is given, but there is no intermediate level. In this case there is an intermediate level closer to conduction band, that is, this is the supplier of our electrons. The electrons in this level can easily go to the conduction band, and then it can provide the required electrons required for the conductivity. Right, so this is the correct answer. So option B is definitely the correct answer for this question. Okay. Now next is, which of the correct diagram for half wave rectifier? So if you see that all the cases this is randomly corrected. Okay, so this should come as the end of the output. Okay, and here it should not be in the middle, it should be at the end of the output. So here as you can see that when the diode is positive here, negative here, it is getting conducted. When it is negative and positive opposite side, it is not getting conducted. So this is how the capacitor should be connected, and this is the correct diagram for the half wave rectifier. This is the diagram for full wave rectifier. Okay, you can consider this one to be full wave rectifier, but in that case you have to have a resistor, not a capacitor. You cannot directly connect a capacitor for a full wave rectifier, but for a half wave rectifier you can directly connect it to a capacitor as well, no problem. In the figure, EV and EC are the valence band and conduction band corresponding to an extrinsic semiconductor. E is the energy state corresponding to the impurity present in the impurity present can be. So as you can see that this is a band diagram, and this is basically a acceptor level. So acceptor level means electrons can jump here easily and create holes in the conduction band. So this is a p-type semiconductor. P-type semiconductor is possible only by doping a trivalent material. So arsenic, phosphorus, antimony, they are all pentavalent. So indium is the answer in this case, that is a trivalent material. Okay, now a match. The following question, column 1 is the list of materials and column 2 the list of energy band gaps E. Identify the correct match. Conductors, insulators and semiconductors. So conductors have 0 band gaps, so basically it is matching with B. Okay, insulators have very high band gap, so it is matching with C, and semiconductors generally in between conductors and semiconductors, so it is matching with A. So 1B, 2C and 3A. So you will see corresponding match, 1B, 2C, 3A. So option D is the correct answer for this question. Hello boys, can anyone say why there is a wave optics in the title? Hello boys, maybe the thumbnail of this video is not updated, but it will be updated. You can see the Chakravyuh semiconductor series. It is available in the at the beginning of the video, right? Hello. There may be some mistake in the thumbnail. When we are doing a live session, we have to upload an image for you to understand which is coming, but maybe by mistake the image was uploaded is incorrect. Okay. 23. When a forward bias is applied to a PN junction, it raises the potential barrier, reduces the majority carrier and current to 0, lowers the potential barrier, rises the width of the depletion region. So when you apply forward bias to the diode, what happens is depletion region decreases, and slowly if you apply sufficient voltage, the depletion region becomes almost 0. Okay, so and basically what does that mean? The potential barrier, the potential gap between p side and n side, that reduces and it becomes 0. That is why the current can pass. So it lowers the potential barrier is the correct option from the given options, given set of options. Okay. The energy gap in a conductor, insulator and semiconductor are respectively E1, E2 and E3. So E1 is smallest and E3 is the greatest. So E1 is the smallest, E3 is the greatest. So definitely option B is the correct answer for this question. P-type semiconductor is electrically positive, negative, neutral. As the temperature increases, it becomes negative. Okay, very interesting question. So P-type semiconductor is electrically what? Positive, because it has more holes, right? That should be the answer. Actually, no. P-type, N-type, PN type, whatever is the diode, whatever is the semiconductor, it is electrically neutral because you are not adding any extra charge to the system. Okay, only thing that you are doing, you are adding impurity to it. Adding impurity does not change its electrical neutrality. Okay, it is still electrically neutral because the suppose you have added phosphorus to a, for p-type you have added say aluminium to the silicon. Okay, the aluminium itself is neutral, the silicon was neutral, so two neutrals they combine. Now their electron densities, electrons and holes created inside the structure, but that does not changes the total number of electrons and total number of holes present in the thing. Density may be different, but protons and electrons that is present inside this, they will be same. Okay, protons and neutrons same means same positive, same negative, so it is still electrically neutral. This question came last year or last to last year's final board exam. Many students answered positive, they got 0 marks, so don't do that. In intrinsic semiconductor at room temperature, the number of electrons and holes are equal, 0, unequal, infinite. So in intrinsic semiconductor at room temperature, the number of electron and holes are always equal. Okay, number of holes, and if it is intrinsic, no matter how high the temperature it is, maybe at high temperature electrons will be highly mobile, but number of electrons and number of holes will always be same. Okay, when a PN junction diode is in forward bias, which type of charge carriers flows in the connecting wire? So PN junction forward biased, ions, protons, holes, free electrons. So basically when the diode is forward biased, free electrons basically carries the current, so obviously free electron is the charge carriers, okay, not holes. A positive hole in a semiconductor is absence of free electrons, an artificially created particle, an antiparticle of electron, vacancy created when an electron leaves the covalent bond. We all know vacancy created by electron coming out of a covalent bond is called a hole. So definitely option D is the correct answer. The energy gap in case of which of the following is less than 3 electron volt? So 3 electron volt, greater than 3 electron volt is for insulators, equals to 0 for conductors, and it is less than 3 electron volt for semiconductor. So which of them is a semiconductor? Aluminium is a metal, so it is a conductor. Okay, iron is a metal, it is also a conductor. Germanium on the other hand is a semiconductor, and copper is another metal, it is also conductor. So only germanium is semiconductor. So for germanium the energy gap is less than 3 electron volt. Next question, last question of the day. Most of the questions are easy from this chapter, that is why we have almost completed the chapter, and also I didn't get desired response from all of you, so that is why we have completed this series quickly. In the depletion region of an unbiased PN junction, the majority charge carriers are only electrons, only holes, both electrons and holes, neither electrons nor holes. Okay, in the depletion region of an unbiased PN junction, electrons and holes they combined and they are dead now. That means there are no mobile charge carriers, so neither electron nor holes are the majority charge carriers in the depletion region. Depletion region means everything is depleted, neither holes are there nor electrons are there, right? Now if you have I have reached the end of this lecture. I was thinking I could extend the lecture up to at least 6:40, but it is over. Most of the questions are memory based and easily answerable, so I guess you have enjoyed this session. If you have any questions, don't forget to mention that in the comment below. I will be try to answer all of your queries, and PDF of this session and all other sessions will be available in our WhatsApp channel very soon, so don't forget to join our WhatsApp channel. Okay, the link of that is given in the description. And definitely, if you like this video, give it a thumbs up and subscribe to our channel if you have not yet subscribed. We are aiming for 50k subscribers as soon as possible, so share it more with your friends so that we can achieve our 50k target very soon. So with this I will close this session, and if you have any questions, obviously you are free to answer in the comment below, right? Bye.